Hey guys, welcome to basically our last lecture. Officially, I would say officially our last optional lecture. Um, well, we will start something new today, and this new thing today it's called the eigenvalue problem for matrices. It's basically the most important chapter from this class. And perhaps I think I'm going to have one more lecture besides this one. So perhaps, I don't know, probably on Thursday or Friday, I will invite you to another lecture. So, you're more than welcome to attend. Let me share the content now. So let's start with the beginning. Let's see what an eigenvalue is, and let's see why these are important. So eigenvalues and eigenvectors. Okay, one request I would have, those of you who have mics on, because I have to look, please turn them off. I would really appreciate that. Okay. All right, so this, like I said, we will talk about eigenvalues and eigenvectors. And let's see, what is the eigenvalue problem about? The eigenvalue problem. And why is this important in linear algebra? Well, the eigenvalue problem, it's probably the most important, like I said, the most important problem in linear algebra. And the central question for this that we want to answer is the following. When, let's say, A is an n by n matrix, so we'll consider an n by n matrix, do non-zero vectors x in Rn exist such that when we multiply A by x, is this Ax a scalar multiple and let's say when I say scalar multiple of x, that is the question. So when Ax is a scalar multiple of x, in other words, we will look for a non-zero vector x, which we will call the eigenvector, such that Ax will be lambda times x. So in other words, we deal with the following problem. So this problem that we're dealing with is Ax equals lambda x, right? And here, this guy, x, will be the eigenvector. And this guy here, lambda, will be the eigenvalue. So in other words, this is the question we want to answer. When Ax is a scalar multiple of x, this eigenvalue will be a scalar. And you will see that this set of eigenvalues, which we'll call this the spectrum of the matrix A, will give you basically all the information you need to know about the matrix. Once you know the eigenvalues, you can know basically everything. You know the characteristic polynomial, you can find the trace, you can find the determinant, and so on. So this is the problem, the eigenvalue problem. Let me tell you a bit of a story. Where did this come from? So x, this like I said, x is the eigenvector corresponding to the eigenvalue lambda, right? So each eigenvalue will see that will have a corresponding eigenvector. The origin, well, this is a nice story. The origin of these two words, eigenvector and eigenvalue, they come from German, right? From the German word Eigenwert, which means proper value. So both of them, they come from, so both words, eigenvalue and eigenvector, come from the German word Eigenwert, and you write it like this. Well, you pronounce Eigenwert, but anyway, this is how you pronounce Eigenwert, which means proper value in German. Okay, so this is the central problem of our discussion for today, and probably for the next lecture as well. So we want to see, like I said, when x is a scalar multiple of the vector x, right? This is what we want to see, and we'll determine when this happens. Okay. Eigenvalues and eigenvectors have many important applications, geometric applications. In fact, they have applications everywhere. And we'll discuss some of them. But now we want to consider the following geometric interpretation. I want to see what does this really mean. So, so if lambda is an eigenvalue, so I'm trying to build some intuition to give you some kind of intuition and some geometric interpretation before I even go and write the exact definition, so that you can have an idea beforehand. So if lambda is an eigenvalue of a matrix A, and x is an eigenvector, of A, corresponding to the eigenvalue lambda. Okay, then the multiplication of x, of the vector x, by the matrix A produces a vector lambda x, right? That is parallel to x. Anyway, for parallel vectors, you can I think you've done this in Calc 3, but anyway, I'll just show you a picture so that you can see. As shown below. So let's see. So let me draw a picture so that you can see it. All right, so let me draw it from here. So we have something like this. And let's just say here is my vector x. Right? And here will be a lambda times x, right? This, let me put another color here. This will be lambda times x, right? I'm just multiplying by a scalar. Okay. And this is the case when ax is lambda x, right? And lambda is positive. But I can also have the case when lambda is negative. So let me draw another picture, which will be similar to this one. This is x, y axis. Anyway, maybe I shouldn't. Okay, maybe I should not mention here x, y axis so that you cannot mess this with. So these are the axes. Okay, and now what I'm going to do, I'm going to draw the same picture. I'm going all the way here. So this will be my vector x, right? And now I want to draw something that's a lambda times x, so a scalar multiple of this vector, but this time it will be negative. So I'm going to go this direction. This will be my vector lambda x. And as you can see here, this will be nothing else than just, this is ax equals lambda x, but this time lambda is negative, right? Anyway, this is easy to see how we represent vectors, right? Okay, and now let's give the actual definition after 10 minutes of talking about what an eigenvalue and eigenvector are. Let me give you the actual definition. But as you can see here at the beginning, basically that will be the definition. But anyway, let's just write it. So definition. And then we'll see some examples how to use how to find eigenvalues and eigenvectors for a matrix. Let A be an n by n matrix. The scalar lambda of A is an eigenvalue. Is an eigenvalue of A. This is very important. When there is a non-zero, and I want to stress this out because it's important, non-zero vector x right, such that, just like we said at the beginning, we have this ax equals lambda x. And now this vector x, so the corresponding, the vector x, let me write it this way. Vector s is an eigenvector of A, corresponding to the eigenvalue lambda, corresponding to the eigenvalue lambda. All right, so that's the definition. I want you to look at it real closely, because this will be very important. We'll see, in fact, there will be a procedure where when we will see exactly how to compute the eigenvalues and the eigenvectors of a matrix through the characteristic polynomial. I'll show you that, but anyway, for the moment, let's just stick with the definition. So that's the definition. And now, before I go and do some examples, let me point out a remark. Since earlier I stressed out that this vector has to be a non-zero vector, and like I said, this is very, very important. So note that that an eigenvector cannot be zero. This is important. So the eigenvector cannot be zero. Allowing, let me phrase it like this, allowing x to be the zero vector would, well, we'll make the definition meaningless, because A0, it's always going to be lambda times the zero vector. That's true for all. This is true for all real values lambda, right? Okay. Now let's see some examples. Example 1. And the first example, like I said, I'm just going to go step by step. I'm just going to tell you to verify that a certain vector is an eigenvector and a certain scalar is an eigenvalue for this matrix. So let me be specific, verifying. So this first example concerns verifying eigenvectors and eigenvalues, right? Okay. All right. So let's consider this matrix. And I'm going to take a 2 by 2 matrix, and we'll take the following matrix: 2, 0, 0, -1, right? And I want to verify, so verify that this vector x1, 1, 0 is an eigenvector of A, right? Corresponding to the eigenvalue lambda 1 equals 2, and that x2, 0, 1 is an eigenvector of A corresponding to the eigenvalue lambda 2 equals -1. Okay, let's see this one here. So as you can see here, basically I'm telling you which one is the eigenvector, which one is corresponding to which eigenvalue, and so on. As you can see, I have two eigenvalues, two eigenvectors. And well, some of you might be tempted to ask, does this have anything to do with the order of the matrix? Yes, you will see that it will have something to do with that. But before we even go in before discussing all this, let's just do this example. Well, so far the only thing we have in hand is just basically applying the definition. There is nothing else we have here. So that's what we need to do. So what do we need to do? We need to multiply vector on the left by a. Let me just say it in words. Multiplying x1 on the left on the left by a produces the following. So it will produce, let's see, ax1 will be 2, 0, 0, negative 1, 1, and we multiply by this vector, right? And now, once we multiply this, keep in mind this is a 2 by 2, and I'm multiplying by this column vector, so it will be 2 by 1, and the result will be what? Based on the multiplication of matrices that we have learned so far, this will be what? It will be again a 2 by 1, so I should expect a 2 by 1. Okay. I want you to do the multiplications and you tell me what do we get? What vector do we get? Two, 0. Indeed. But I want somebody else to answer, not just only Liliana. Anyway. All right. And as you can see, I can factor out 2, and I can write this as 2 times 1, 0. Right? Guess what? At this point, I can say that, look here, this is the eigenvalue. And this guy right here is the eigenvector. Right? Okay. All right. So now let's see for the second one. Okay, let me just write it. So x1, which is 1, 0, right, is an eigenvector of A corresponding to the eigenvalue lambda, let's call this lambda 1, since it's the first eigenvalue, let's say equals 2. So that's what we proved here, as you can see. Right? Okay. Now, let's see if similarly for the second one, right? Similarly, multiplying x2 on the left by A will produce what? Produces, so let's do this again. AX2, we'll write the matrix again, 2, 0, 0, negative 1. And this will be multiplied by the second vector, which we said that it's 0, 1. So again, this will be a 2 by 2 multiplied by a 2 by 1. The result will be a 2 by 1 and will be what vector? Can you tell me? Will be 0, 2, 0, 1, 0, are you sure it's 0, 1? 0, negative 1, correct. And if you look here, this will be negative 1. We can factor this out times this. And again, the same story here. This is what we call the eigenvalue. Eigenvalue, right? And this is what we call the eigenvector. So x2, 0, 1 is an eigenvector of A corresponding to the eigenvalue and let's say lambda 2 equals negative 1, and that's it. So this is how we deal with and verifying that something is an eigenvalue or an eigenvector. As you can see, it's pretty straightforward. There's just a multiplication of the matrix by the vector. Like I said, more difficult it will be when we will try to find the eigenvalues and the eigenvectors without even knowing anything about them. But anyway, we'll get there. Now let's see another example. I'm going a bit slower now at the beginning so that you can grasp everything that I say. Again, I'm verifying eigenvalues and eigenvectors. Verifying okay, and now I'm going to take another 2 by 2 matrix. I will take a 3 by 3 matrix. Let me consider the following. Let A be the following 3 by 3 matrix. 1, negative 2, 1, let's say. 0, 0, 0, 0, 1, 1. And for this matrix, so again, this is a 3 by 3. Let's keep that in. Verify that x1, let's say negative 3, negative 1, 1, and x2 is 1, 1, 0 are eigenvectors of A, and find their corresponding eigenvalues. So we don't know which are the eigenvalues, so we have to find them corresponding eigenvalues. Anyway, this is a simple example. All right, so what are we left to do? Just apply the definition, that's it. Again, we multiply x1 on the left by A. Again, the same story. Similarly, we have, what do we have? We have that AX1 will be equal to, so let's write this matrix here, 1, negative 2, 1, 0, 0, 0, 0, 1, 1, and we multiply by this first vector. So 3 by 3, the first vector was negative 3, negative 1, and 1. And if when we multiply this, so this is a 3 by 1, can you tell me what do we get? We get again a 3 by 1. Okay, I want you to do the computations, and I want you to tell me what column vector do we obtain here? Are you sure, Andy? Let's see. I see Blair got something. Let's see somebody else. Andy, okay. Angel, okay. So at this point, this is 0, 0, 0, right? It's a 0 vector. And now the question is, can I write this as I can write this easily as 0 times negative 3, negative 1, negative 1, right? In other words, so x1 is an eigenvector of A, corresponding to which eigenvalue? Can you tell me? Lambda 1 will be what? Can you tell me? Okay. 0, exactly. As you can see here, this is the eigenvalue. And this guy here is the eigenvector. Right? All right. Now, similarly, again, multiplying the x2 on the left by A will produce the following. So we have that ax2 will be 1, negative 2, 1, 0, 0, 0, 0, 1, 1. And this time, we will multiply this by this, 1, 0, 0. Again, this is a 3 by 3 by a 3 by 1. And this will give us what? This will give us, well, can you tell me what this will give us what? What vector? Again, it will be a 3 by 1. Zero, zero, zero. Not quite, almost, yeah. Angel says, and Liliana, correct. It's 1, 0, 0. Which can be written as 1 times 1, 0, 0. Again, the same story here. This is the eigenvalue. And this is the eigenvector. Well, by just multiplying, Neil. So you just multiply everything here. 1 times 1 plus negative 2 times 0 plus 1 times 0, which will give you 1, the first one, and then you just go by the usual multiplication of matrices. If you didn't get this 1, 0, 0, probably you messed up something in computations, but it can be easily fixed. Okay. So x2, 1, 0, 0 is an eigenvector of A corresponding to the eigenvalue lambda 2 equals 1. And that's it. Again, we verified that this happens. All right, now let's get, so I believe this is easy at this point. It's quite straightforward. Now let's talk about the eigenspaces. Well, the story is the following here. Well, if you look at examples number 1 and number 2, just by looking at them, you see, we said that you see for each eigenvalue, we only had one eigenvector. So, or each eigenvalue was corresponding to one eigenvector. But now, for instance, we can have the following. If A is an n by n matrix with an eigenvalue lambda and a corresponding eigenvector let's say x, then every non-zero scalar multiple of x is also an eigenvector of A, right? So we have seen this. And now, okay, I don't want to get into the proof of this, but it's quite easy to see. But I want to mention the following. In other words, the set of all, how should I phrase it, of all eigenvectors of an eigenvalue lambda together with the zero vector, is a subspace of Rn. And this special subspace we will call, what should I, okay, this, I'm going to phrase it just like that. This special subspace is called the eigenspace of lambda. All right, let me summarize this. We have the following theorem. Let me write in mathematical words. In other words, this is eigenvectors of lambda form a subspace. Okay, the theorem states the following: if A is an n by n matrix with an eigenvalue with an eigenvalue lambda, then the set of all eigenvectors of lambda together with the zero vector, and let me express this in the following way. So this set, the set of all vectors x, where x is an eigenvector, and now I'm going to reunite this with the zero vector. This is, so this guy is a subspace, is a subspace of Rn. And this is what we call the eigenspace of lambda. Okay, let me write it here. This guy is the eigenspace of lambda. This set right here, right? So I'm considering the set of all vectors, all eigenvectors, and I'm just reuniting with the yes, exactly. Yes, Kobe, yeah. All right, and now let me, before I even give you the how to find the eigenvalues and the eigenvectors, or maybe, yeah, actually I should do it. How to find the, so let me answer this question since I don't want to do all, go around the bush too much. Just let me stick to the point. How to find, so we want to answer this question. How to find eigenvalues and eigenvectors. That is a question we want to answer. Well, as you can see here, I'm going to do the following. Let me, before I even go and explain the theorem, to find the eigenvalues and the eigenvectors of n by n matrix. So let me consider, let A be an n by n matrix, and also let I be the n by n identity matrix. Let me remind you that the identity matrix looks something like this. 1, 0, 0, 0, 1, 0, 0, 0, all the way 1. So all the elements on the main diagonal are 1. And now I'm going to do the following trick. So we rewrite, rewriting AX equals lambda x, we will write this in the following way as, and pay attention here, I'm going to do this magic trick. Lambda times the identity x times x will be AX. And rearranging will give us lambda times the identity minus A times X will be the 0 vector. So this is how we rearrange this. So in other words, this is, if you look at this closely and if you write this, this is nothing else. So if you write this component-wise, this is nothing else than just a homogeneous system of equations. So this is a homogeneous system of equations. That's what this is. And we know that this homogeneous system of equations, let me remind you from the systems of equations, so this goes back to lecture number 2, long time ago. Remember that the system of homogeneous equation, the homogeneous system, the homogeneous has non-zero solution, has, and let me point this out, has non-zero solutions if and only if, so when I say if with double F, I mean if and only if, so it goes both ways. Probably you're used with this by now. If and only if the coefficient matrix, the coefficient matrix lambda I minus A, so this matrix is not invertible. In other words, when this matrix is not invertible, when its determinant is 0. Which means, let me write here, that is if and only if its determinant is 0. Keep that in mind. In fact, you will see when we let's translate this formally. And this could be formally translated into the following theorem, which will concern eigenvalues and eigenvectors of a matrix. Of a matrix. Okay. And then we'll see some examples how to apply this theorem. Let A be an n by n matrix. And we have the following. 1, an eigenvalue of A is a scalar lambda such that, guess what, determinant of lambda times the identity minus A is 0. In other words, this theorem tells us how to find the eigenvalues of a matrix. In other words, you look at this matrix, lambda times identity minus A, you take the determinant, and then you find the eigenvalues. Anyway, you will see examples. It's quite easy. The second one, the eigenvectors of A corresponding to lambda are the non-zero solutions of this guy here, lambda times the identity minus A times x will be 0. So this is how we find the eigenvectors. Once we determine the eigenvalues, then we find the corresponding eigenvectors. And now let me point out a remark here before we start doing some examples. And then after finding examples of eigenvalues for matrices, then we'll see that we can find eigenvalues and eigenvectors for linear transformations associated to matrices. Anyway, we'll get there, but before that, let me point out this remark. The equation, the determinant of lambda I minus A equals 0, is what we call is the characteristic polynomial. Is the characteristic. No, let me write it here. Is the characteristic equation, let's say, of A. Moreover, when we expand this, when expanded to polynomial form, the polynomial, I'm going to write it in this way, P A of lambda, which is, so this is what we call the characteristic polynomial, which is the determinant of lambda times I minus A, will have the following form. It will look like, it will be a polynomial of degree n, and it will look like this. Lambda to the power n plus some coefficient c n minus 1 lambda to the power n minus 1 plus, and we go all the way, c2 to lambda 2 squared plus c1 lambda 1 lambda plus this coefficient c0. So this guy is what we call the characteristic polynomial. And in fact, I will show you more examples of the review session before the exam, where how to deduce facts about eigenvalues using the characteristic polynomial. And in fact, there will be a connection between these. We can find eigenvalues easily. You can find a trace. You can find a determinant using the characteristic polynomial. But anyway, we'll see this maybe at the review session, where I'll do more problems. So this is what we call the characteristic polynomial of A. So the eigenvalues, so that's my point here. So the eigenvalues are nothing else, just the roots of the characteristic polynomials. So the eigenvalues of an n by n matrix A correspond to the roots of the characteristic polynomial of A. Polynomial of A. In other words, you want to find the eigenvalues, you look at the characteristic polynomial, which is this guy right here, right? You look at the roots or zeros of this guy. In other words, eigenvalues can be found when we set this PA of lambda equal to 0. So for example, if you have this polynomial of degree 3, there is a chance that you might have at most 3 roots for this guy, right? Anyway, let's see some examples now. I want to illustrate all these techniques. So example, I don't recall which example number was this, probably example 4 or 3, I think. Anyway, I'm bad with numbers. And now this will concern, what time is it? Oh my. Find the eigenvalues and corresponding eigenvectors I would like you to turn your cameras on now. I think we still have like 20 minutes left. And the corresponding eigenvectors of the following matrix. A is 2, -12, 1, -5. Okay. And now let's see the solution for this. Like I said, the only thing we need to do is just to look at this guy right here. A lambda is nothing else than just the determinant of lambda times the identity. In our case, it's the 2 by 2 identity. Keep in mind that this is a 2 by 2 matrix minus A. And now let's do the computations. This will be the determinant of lambda minus 2, 12, -1, and lambda plus 5, right? And when we compute the determinant of this, keep in mind that this 2 is this is the determinant, and this will give us what? Will give us lambda squared. So it's lambda minus 2. Okay, let me write it. I don't want to make any mistakes. So it's lambda minus 2 times lambda plus 5 minus plus 12, right? So this will give us what? This will give us lambda squared plus 3 lambda minus 10 plus 12. Okay. Okay. So this is just lambda plus 1 times lambda plus 2. And now we set this equal to 0, right? So once we set this equal to 0, so the characteristic equation is what? Is lambda plus 1 times lambda plus 2 equal to 0, which gives us what? So from here we'll infer that what? Lambda 1 is what? -1, and lambda 2 is -2. So these are the eigenvalues of A. Right? And now for each eigenvalue, we need to find the corresponding eigenvector. So we need to find a corresponding eigenvector. In other words, we need to solve to find the corresponding eigenvector. We need to solve the system, the homogeneous system, lambda times identity minus a, x equals 0 twice. So we need to solve this twice. Okay. Well, and now we need to solve for the first one. Let's say for this case, for lambda 1 equals -1. Oh my. There will be some computations here. Okay, let me write like this so that it wouldn't be lambda equals lambda 1. So let's start with this one first. So we know that lambda 1 is -1, so we will have -1 times the identity minus a. This will give us this matrix -1, -2, 12, -1, -1 plus 5. And this will be the following matrix. -12, -3, 12, -1, and 4. And keep in mind here this, which row reduces to what? Well, as you can see, we can factor something out there. We'll reduce to -1, 4, 0, 0. Keep in mind that you still have to do the row reduction for this matrix. And this will reduce to this matrix, showing that once you solve this system and showing that once you look at this equation here, right? And when you plug it in, okay, let me write it so that showing that the system -1 times I 0 has the following solution. And once you multiply this, so this x is x1, x2, has solutions. You will see it will have infinitely many. Anyway, we'll have so it will have, so okay, so it will give you x1 equal, yeah, -4x2 will be 0, right? And now let's say x2 to be t, with t real number. And once we can conclude that, that what? That every eigenvector of lambda 1 is of the form let's say, let's write here, x is, I'm going to write it like this, x1, x2, which will be 4t and t, and we can factor t, so this is t times 4, 1, the vector. With t, of course, has to be different than 0, right? So this is the corresponding vector, eigenvector for lambda 1 equals -1. And now let's see, for lambda equals lambda 2, what was the second eigenvalue? It was -2, right? Yeah. Let's see for this one. So we'll do the same thing. We'll have -2 times the identity minus a, and this will give us, let's see, some computation. So -2, -2, -2. Wait, what was the matrix A? 2, -12, 1, -5. Okay. So it's 2, -2, 12 here, -1, -2 plus 5. Okay. And this will give us, if please correct me if I'm doing something wrong in computations, but this will be -4, 12, -1, and 3. Okay. And again, this will row reduces to, which row reduces to let's see, 3. Okay, so I have to do a 0 there. Okay, this is easy to see, that will row reduce to 1. This will be -3 and 0, 0. Okay, great. Again, if we write showing that the system -2 times the identity minus a times x, which is 0, has the solution, and again this will have has solutions of the form what? Let me see. So it will be x1 will be something like 3t, and x2 equals t with t real, right? Something like this. Anyway, I'll leave it to you as an exercise to do the computations to verify everything. But I don't, let me see. Yeah, I think that should be okay. So we can conclude now that every eigenvector of lambda 2 is of the form x, let's write it like this, x1, x2 equals this guy 3t, t, and we can factor here, this is t, 3, 1. And that's it. Oh my, that was something. You see. Now I'm going to give you the general strategy to find the eigenvalues and the eigenvectors of a matrix. And probably I'm going to leave to you as an exercise, or maybe we'll do it for next time, for Thursday or Friday. If you like to attend, I will continue from there anyway, to find the eigenvalues for a 3x3, and of course, in their corresponding eigenvector for a 3x3, and even maybe a 5x5 matrix. Oh my goodness. We'll see, maybe, I don't know, I'm not sure if I'll do a 5x5, but anyway, that will be atrocious to do. All right, so the general strategy for finding eigenvalues and eigenvectors. So let A be an n by n matrix and now the first one will be the following. So the first step, okay, let me write like this. Step 1, form the characteristic equation determinant of lambda times the identity minus a equals 0. And keep in mind that this is nothing other than just equating the correct characteristic polynomial with 0, right? So we first form the characteristic equation, and this will be, like I said, it will be a polynomial of degree n in the variable. So this is a polynomial. So the characteristic polynomial is a polynomial of degree n, in the variable lambda. Okay, so this is step 1. Step 2, find the real roots of the characteristic equation. So the characteristic equation is this one above here. Characteristic equation. These are the eigenvalues of A, right? Step 3, which will be the final step, once you find the eigenvalues, will be for each eigenvalue, lambda, let's say, find the eigenvectors corresponding to lambda i's. Let's say we have a bunch of eigenvalues depending on the degree of the polynomial. By solving the homogeneous system, you see at the end of the day, everything boils down to solving systems of linear equations. And I told you from the beginning to pay attention to methods, to row reduction methods and everything. We have the row echelon method so that you can easily operate in this case, for example. By solving the homogeneous system, lambda I times the identity minus a times x is 0, right? This is a vector here, keep in mind. This is a matrix. This is a vector. And of course, this will be a vector, the 0 vector. So that will be my homogeneous system I need to solve, right? And let me be specific here. This can require row reducing an n by n matrix. And God knows how many examples of this kind of. So if you have, even by now, but I've seen based on your exams that you don't have any problems with row reducing matrices. But if you still have problems with this, I would suggest you go back to old videos that we basically used row reduction or to row echelon form, row reduced echelon form many times. I suspect in almost every lecture. Okay, so this can require row reducing an n by n matrix, and okay, the reduced row echelon right form. So the reduced row echelon matrix that we obtain must have, okay, must have at least one row of zeros. At least keep in mind this, one row of zeros. Keep in mind this. This is important. All right. So that's the strategy. I want you to look at it again. See, the general strategy, there are 3 steps. Once again, the first step, you look at the characteristic polynomial and you set up the characteristic equation in this way. So it's just the determinant of lambda times the identity minus A. You set it equal to 0. You find the eigenvalues, lambdas. And then you find, this is step 2. And for step 3, for each eigenvalue, for each root, real root that you found in the previous step, you just find the corresponding eigenvectors by just solving the homogeneous system, which is this one right here, right? And again, this, like I said, this is required for you to reduce, to row reduce some matrices there. And you reduce it in such a way that they will obey this. In other words, must have at least one row of zeros. Okay, guys, I think I'm going to stop. Let me give you, for you as a homework, and probably I will continue with this next time. So example number, I don't recall, example, what number is it? Number 4, I think. Okay. Example number 4, again, find the eigenvalues and the eigenvectors of the matrix A equals 2, let me take a 3 by 3 this time, 2, 1, 0, 0, 2, 0, and now let me take 0, 0, 2. Okay, I want 2 on the main diagonal. Okay, guys, thank you very much. I will stop here for today. Like I said, next time I will continue with this. Thank you very much.